Have you ever wondered how AI learns to see, without being explicitly told what to look for? Today, we're diving into a groundbreaking study that's reshaping how we train transformer models, those powerful engines behind image recognition, language processing, and more. Let's break down the science behind transformers without normalization and why it's a game changer. So, what's the big deal with normalization? In machine learning, normalization is like adjusting the brightness of a photo to make details clearer. But this research asks, what if we skip that step? By removing traditional normalization techniques, like layer normalization, and replacing them with something called DynTanh, the team discovered surprising improvements in how models understand images. The study compared two approaches, IJEPA-Tanh and IJEPA-LN. Think of them as two versions of the same model, but with different training wheels. IJEPA-LN used the classic layer normalization, while IJEPA-Tanh swapped it out for this new DynTanh method. The goal? To see which one could learn better representations of images, like how humans recognize objects even in blurry or partial views. Here's where it gets fascinating. When tested on ImageNet, the IJEPA-Tanh model smashed records. Its linear probe accuracy, essentially a test of how well it can classify images, jumped from 12.5% to a stunning 32.2%. That's like a student going from barely passing to acing an exam. The team also found that IJEPA-Tanh was better at tasks like depth estimation, predicting how far objects are in a scene. Imagine self-driving cars or robots using this tech to navigate the world more accurately. But why does this matter to you? Well, these models are the backbone of AI applications we use daily, from photo tagging on social media to medical image analysis. By simplifying the training process and improving accuracy, this research could lead to faster, more efficient AI that works better with less data. Let's get technical. Normalization, while stabilizing training, has a hidden cost. It flattens the energy hierarchy of visual features. Think of it as dimming a spotlight on a critical detail to make the entire scene even. This masks the natural importance of elements like textures or edges, forcing the model to rely on statistical patterns rather than true understanding. The researchers uncovered a critical flaw. Standard normalization caused checkerboard artifacts in loss maps. These grid-like patterns, unrelated to actual image content, revealed the model was confused by uniformity. DynTanh, however, preserved the natural energy distribution, letting the model focus on semantically rich regions, like a human would. The proof is in the pudding. IJEPA-Tanh boosted ImageNet accuracy from 38% to 42.7%, and improved depth estimation by 0.08 on average. These aren't tiny tweaks, they're game changers. The model's loss distributions also showed a longer tail, indicating it captured more nuanced, semantically meaningful patterns during training. The study also uncovered some surprising quirks. For example, the way data is shuffled during training, like mixing up image batches, had a huge impact on performance. A simple fix, like reshuffling data with replacement, prevented the model from memorizing the training order, a common pitfall. So next time you see an AI model doing something impressive, remember, behind the scenes, researchers are constantly tweaking these invisible knobs to make machines smarter. And who knows? Maybe the next big breakthrough is just a small change away. Thanks for watching. If you want to dig deeper into how AI learns from unlabeled data, hit subscribe and let me know what you'd like to explore next. Until then, keep wondering, because the future of AI is still being written.